All right, welcome back to the deep dive. We are diving into some really interesting machine learning research again today.
Absolutely.
So today's paper is titled ONE, Evaluating LMMs for Capability, Integration, and Instruction Grounding. And I think you'll agree this is a pretty cool one.
Oh, definitely. It's really timely, too, given all the hype around LMMs.
Yeah, for sure. For those just tuning in, by the way, LMMs stand for Large Multimodal Models. And basically the idea is you're teaching AI to, not just read text, but to actually make sense of images too, like really understand what they're seeing.
Right. It's kind of like giving language models eyes, so to speak. And this paper, it goes beyond the usual, can it tell a cat from a dog kind of test.
Right. So what's MOAD all about then?
Well, MOAT, it stands for Multimodal Abilities Test. It's this new benchmark, right? And it's really trying to get at how well these LMMs can actually combine different visual skills, not just, recognize an object, but also count things, understand where things are in relation to each other, read text in an image, all that good stuff.
And then use that information to actually follow instructions.
Exactly. That's a huge part of it. Like, imagine you're trying to put together some furniture, right? You've got the instruction manual, maybe some diagrams, a bunch of parts. You got to be able to, look at the pictures, read the steps, and actually understand how it all fits together.
So it's about taking visual information and turning it into action.
You got it. And what's really neat is the paper, it lays out this whole taxonomy of what they call fundamental vision language capabilities. They've got 10 of them.
10. That's a lot.
It is, but it makes sense when you think about it. Under recognition, you've got counting OCR, that's optical character recognition, so like reading text and understanding charts and visualizations. Then for spatial understanding, there's things like knowing how objects are positioned, understanding how shapes change when you rotate them, and even grasping those spatial quantities, like knowing what's bigger or smaller.
Okay, so it's getting pretty granular.
Oh, for sure. And then you've got instruction grounding, so understanding instructions given as text and even as images. And finally, they've got this category for handling more complex scenarios, like finding specific info in a really busy image and understanding how multiple images relate to each other.
Okay, so they're really putting these LMMs through the ringer. What do they find?
Well, the big takeaway is there's still a pretty big gap between these models and us humans.
No surprise there.
Right. But it's good to quantify it. So they had humans try these MOAT tasks and got an average accuracy of like 82.7%. Pretty good, right? But the best LMM, OpenAI's O1 model, it only got to 38.8%.
Wow, that's a pretty stark difference. So even our best AI is still, struggling to really get a grip on all this visual stuff.
Yeah, just goes to show how complex visual intelligence really is. I mean, we take it for granted as humans, but it's an incredibly complex process.
And this is where I think it's helpful to, zoom out a bit and look at how we even got to LMMs in the first place.
Absolutely. So, for a long time, AI research in vision and language, they were kind of separate things. You had natural language processing over here doing amazing things with text, and you had computer vision over there doing its own thing with images.
Right. So it was like two different parts of the brain not really talking to each other.
Exactly. But then researchers started thinking, hey, why not combine these superpowers? And that's how we got LMMs. Basically, they took these large language models, which were already really good at understanding and generating text, and they figured out ways to hook them up with visual components, these things called vision encoders.
So like adding a visual input to the language model?
Yeah, and it wasn't as simple as, plugging in a camera. They had to come up with clever ways to make these different parts of the model actually talk to each other. Things like adapter designs, Q-former, Q-llama, those kinds of things, or even just using more straightforward methods like multi-layer perceptrons. A lot of innovation went into that integration process.
So this idea of combining vision and language, it's been brewing for a while, and as these models got better, we needed ways to test them, right?
Totally. And that's where benchmarks come in. Early on, you had benchmarks like VQA, which stands for Visual Question Answering. Basically, you'd show the model an image and ask it a question, and it had to give you an answer.
It's like, what color is the ball? That kind of thing.
Yeah, exactly. And VQA was a good starting point, but the questions were often pretty basic. Then you had other benchmarks like OKVQA, which tried to be a bit more challenging, and later on, things like MMMU, MMVet, and Seedbench, which tried to test a wider range of multimodal skills.
So the benchmarks were getting tougher. But what's the problem with those older benchmarks?
Well, the creators of MOAT, they argue that those benchmarks, even the newer ones, they often fall short in a couple of key ways. First, they don't really test the integration of multiple visual skills within a single task. Like you might have one question that's all about object recognition and another that's just about spatial reasoning, but not many that require both at the same time.
And second,
they don't do a great job of evaluating how well models can actually ground instructions. It's not enough to just understand what's in an image. You need to be able to understand what you're supposed to do with that information based on instructions.
right, like actually using the information to complete a task.
Exactly. And that's really where MOAT comes in. It's designed to address those limitations and push LMMs to a higher level of visual understanding and reasoning.
Okay, so we've talked about why MOA is important and how it came about. Let's dig into the specifics a bit more. You mentioned 3 key characteristics that set it apart. Could you walk us through those?
Sure. First, as we've discussed, MOAT questions are designed to require the simultaneous integration of multiple visual skills. So you might need to recognize an object, understand its spatial relationship to other objects, read some text in the image, and then use all of that information to follow a set of instructions. It's really pushing the boundaries of what these models can do.
So no more easy questions.
Nope. And second, MOAT really focuses on the explicit evaluation of grounding both visual and complex text instructions. This means the model not only needs to see what's there, but also understand what actions to take based on those instructions. So it's not just about perception anymore, it's about turning perception into action.
Like a real-world robot would need to do.
Exactly. And finally, the use of close-ended questions solvable with provided knowledge and hints ensures that the benchmark is really focusing on the core vision language abilities and not getting sidetracked by other factors like general knowledge or the modder's ability to generate creative text.
Right, so it's a more controlled test of these specific skills.
Exactly. And that's really important for getting a clear picture of where these models excel and where they struggle.
You also mentioned that the paper breaks down performance across these 10 fundamental vision language capabilities. Can you give us a quick recap of what those are and maybe highlight some of the key findings?
Yeah, sure. So we've got counting, which is, well, pretty self-explanatory, OCR or optical character recognition for reading text and images. Understanding charts and visualization, so making sense of those more abstract graphical representations. Then there's a bunch related to spatial understanding, knowing how objects are related to each other, understanding how they look when rotated or viewed from different angles, and grasping those spatial quantities like bigger or smaller.
Sounds like a lot of geometry involved.
Definitely.
Yeah.
And then there's instruction grounding, which involves understanding instructions given in both text and image form. And lastly, we have tasks that involve searching for specific information in busy scenes and understanding how multiple images relate to each other.
A pretty comprehensive set of skills.
Yeah, it covers a lot of ground. And what they found was, well, across all 10 of these capabilities, there was a significant gap between how humans performed and how the LMMs performed. But some areas were particularly challenging for the models.
Like what?
Well, counting, for example, was surprisingly difficult for many of the models, especially when the objects to be counted were scattered around in a complex scene. And grounding text instructions, that was another area where they really struggled. This suggests that even seemingly basic tasks like counting or following simple directions can be quite challenging for these models when they're in a visual context.
So it's not just about recognizing objects anymore, it's about understanding how those objects relate to each other and how to interact with them based on instructions.
Exactly. And that requires a much deeper level of understanding than just being able to label things in an image.
One of the more interesting parts of the paper was the analysis of proprietary versus open source models. What did they find there?
So as you might expect, the proprietary models, the ones developed by companies like Google and OpenAI, they generally performed better overall. And the researchers think that's likely due to the fact that they've been trained on much larger data sets and have a lot more parameters, which gives them more capacity to learn complex patterns.
So bigger is better, at least in terms of raw performance.
It seems that way, for now at least. But what was interesting is that within the open source models, they saw a pretty clear trend. As the number of parameters in a model increased, so did its accuracy on MOA. This suggests that scaling up these open source models is a promising avenue for further improvement.
So there's still hope for the little guys.
Absolutely. And it also highlights the importance of making these large-scale models more accessible to researchers and developers who might not have the resources of a giant tech company.
It was also fascinating to see that no single model was the best at everything. Different models had different strengths.
Right. Like OpenAI's models were really good at understanding charts and diagrams, as well as handling those 3D spatial transformations in multi-image tasks. But Claude 3.7, that model excelled in understanding spatial quantities and grounding both text and visual instructions. And Gemini, along with some OpenAI models, was quite good at OCR.
So it's like a diverse ecosystem of models, each with its own unique capabilities.
Yeah, and that's actually a good thing. It means there's a lot of room for innovation and specialization. It also highlights the need for more balanced development efforts. Instead of just focusing on making models bigger and bigger, we also need to focus on improving specific capabilities and making sure these models are well-rounded.
Right, like a decathlon for LMMs.
Exactly.
Yeah.
And speaking of specific capabilities, there were some areas where pretty much all the models struggled, regardless of their size or origin. Counting, as we mentioned earlier, was a consistent challenge, especially in complex scenes. And they also had a tough time with relational awareness, understanding how objects are positioned relative to each other.
And instruction grounding, both text and visual, continued to be a major bottleneck.
Yeah, that was a persistent theme throughout the paper. These models, they can see what's there, but they often struggle to understand what to do with that information based on instructions.
Like they're missing that crucial link between perception and action.
Exactly. And that's a pretty fundamental challenge if we want these models to be truly useful in real-world scenarios.
The paper also looked at how chain-of-thought reasoning affected performance. That was pretty interesting.
Oh yeah, that was a bit of a surprise. Chain-of-thought prompting, it's been really effective for language models. The idea is you get the model to think step by step, like, okay, first I need to do this, then I need to do that, and that helps it reason more effectively.
So they tried that with the LMMs?
Yeah, and what they found was, well, it didn't always help. In some cases, it didn't really make a difference, and in some cases, it actually made things worse, especially for those vision-centric tasks like grounding instructions.
Really? Why would thinking step by step make them worse at following instructions?
Well, the researchers think that if the model's initial understanding of the visual scene is flawed, then even if its reasoning process is logically sound, it's going to end up with the wrong answer. It's like giving someone bad directions and then telling them to think carefully about how to follow them. They're still going to end up lost.
So garbage in, garbage out, even if you reason carefully about the garbage.
Pretty much. And this really highlights the importance of getting that initial visual perception right. We need to make sure these models can accurately see and interpret the visual world before we start layering on complex reasoning processes.
So it's back to basics.
In a way, yeah. We need to focus on improving those fundamental visual capabilities before we can expect these models to handle complex real-world tasks.
It seems like MOA is a valuable contribution to the field, really highlighting where we need to focus our efforts in LMM development.
Totally. It's a much-needed reality check. It shows us that while LMMs have made impressive progress, there's still a lot of work to do before they can achieve the kind of robust, human-level visual intelligence we're aiming for.
So for our Novel Notions segment today, I thought it would be fun to brainstorm some potential research directions based on the challenges and findings highlighted in the MO8 paper. What are your thoughts?
Let's see. One thing that really stood out to me was the persistent difficulty with instruction grounding. It seems like these models, they often struggle to bridge the gap between abstract language or even visual cues and concrete actions in a visual scene. So what if we explored the idea of embodied VL agents with active querying for instruction grounding?
Okay, I'm intrigued. What do you mean by that?
So imagine an LMM, right? But instead of just passively observing an image or a video, it's actually embodied in an agent, like a robot arm, with a camera that can actively interact with its environment. Now, when it receives an instruction, if there's any ambiguity, it can actively query for clarification, like, are you referring to the red block or the blue one? Or maybe even physically manipulate objects to understand their properties or spatial relationships.
So like a more interactive and inquisitive approach to understanding instructions.
Exactly. And this is something we humans do all the time, right? When we're unsure about something, we ask questions, we explore, we try things out. So why not give these models the same ability? It could significantly improve their ability to ground instructions accurately in real-world scenarios. Of course, this would require advances in both LMMs and embodied AI, and we need to develop new evaluation metrics that go beyond just task completion and actually assess the quality and efficiency of these clarification queries. But I think it's a really promising direction to explore.
It's definitely an intriguing idea, moving beyond passive processing to active engagement for better understanding. What other novel notions come to mind based on MOAT's findings?
Well, another area where UMA revealed consistent weaknesses was in spatial understanding. Tasks involving things like counting objects, understanding their relative positions, and handling those 3D spatial transformations. Those were all consistently challenging for the models. And this got me thinking, what if we moved away from the idea of a single monolithic visual encoder and explored architectures with specialized modular components dedicated to different aspects of spatial reasoning?
Okay, I'm following you. Break it down for us.
So imagine, instead of one big visual encoder trying to do it all, we have separate modules, each optimized for a specific spatial task. Like you could have one module that's specifically designed to handle 3D spatial relationships, another that's really good at understanding of rotations and scaling, and maybe even a dedicated module for counting that's more robust to issues like objects being fragmented across image tiles. This kind of modular approach, it draws inspiration from ideas in modular neural networks and attention mechanisms, and it could lead to more interpretable and robust spatial reasoning.
So, like dividing and conquering the spatial reasoning problem.
Exactly. And the findings from the MOAT paper, particularly the fact that those spatial capabilities were consistently weak and that image tiling seemed to negatively impact counting accuracy, they suggest that a more refined approach to spatial representation is needed. Of course, the big challenge with this approach would be figuring out how to effectively coordinate and integrate the outputs from these different specialized modules. How do you get them to work together to create a coherent understanding of the scene? That's a non-trivial problem, but I think the potential benefits in terms of performance and interpretability are significant.
It's a really fascinating idea, and it highlights how much we still have to learn about how to build truly intelligent systems that can perceive and understand the world the way we do.
Absolutely. And that's what makes this field so exciting. There's so much we don't know. And every new paper, every new benchmark brings us a little bit closer to understanding the complexities of visual intelligence.
If you want to learn more about this research and the MOA benchmark, we highly recommend checking out the full paper. You can find a link in the show notes.
Definitely worth a read. It's a dense paper, but it's full of fascinating insights.
And on that note, here's a final thought to leave you with. If even our most advanced AI models are struggling with seemingly simple tasks like accurately counting objects in complex scenes, what fundamental breakthroughs do we need to make in our approaches to architecture, training data, or learning algorithms to finally achieve that elusive goal of human-level visual intelligence? It's a big question, but it's one that's worth pondering. Thanks for joining us on this deep dive.
Thanks for having me. Always a pleasure.
And to all our listeners, thanks for tuning in. We'll catch you next time on The Deep Dive.